Hi. Purpose of this recording is to introduce a simulation that will help with the quiz on the modern theory of atoms, specifically with respect to lasers. So from your browser, let's look for a PhET simulation called lasers. Now, you won't find this on the regular website for PhET because it's a legacy version, but we can find it if we search for it. Because it's a legacy version, um, it may or may not work well on your browser. I found that this version runs really well on most browsers, but some of the browsers struggle with Java. So go ahead and select the first choice. Okay, so now our goals, we have three goals for this video. One is to talk about spontaneous emission of radiation, then stimulated emission of radiation, and then finally, multiple atoms and lasing. So let's start off with the first part. Right now, we can see that you've got a lamp that's sending in photons. We have an atom that's in a vessel, a containment vessel, and that the color of the light that's emitted by the atom is the same as the color that's emitted by the lamp. So when a photon comes in from the lamp and it makes contact with the atom, it has a good shot of being able to get its energy to transfer into that of an electron. So quantum mechanics is saying that each photon has a finite amount of energy. And in this case, because it's red light, it has an energy level that matches up with the energy level of the atom. Let's see what happens if we change the color of the lamp. You can see the energy of the photon no longer matches up with the energy level that, or the transition between energy levels from the ground state to this first excited state. So when we adjust the color of the lamp, you can see that now the energy for each photon is decreasing. And then it's unclear if we can stop. So I'm going to keep changing until I see the blink happen. And then we can double check and make sure this is working, because if we have a direct collision with the atom, it looks like I'm missing a little bit in this case. So let me try and dial that in a little bit better. There we go. So I think this should work. Yeah, here comes a photon. And if there's a direct hit with the atom, then the electron absorbs the photon, kicking it up into an excited state. And then later, at some random time, it's going to spontaneously emit. Now, let's take the lifetime and turn that way down and see what happens to the time it takes. This time, a spontaneous emission happens immediately after getting excited. Okay, good. So right now, this is all spontaneous emission of radiation. How can you tell? Because they go off in random directions. Let's take a look at a situation where we can stimulate the emission of radiation. If we can get the electron to stick around in that excited state for a little bit longer, and we increase the frequency of the number of photons that we're bringing in, now you can see that almost all the radiation that's emitted is stimulated. Because when stimulated, what happens is that the incoming photon has the same energy level as the excited state of the electron. And when it passes by, it triggers the emission of radiation from that electron. But in shorthand, it all means the same thing. It means that we're going to have quite a few stimulated emissions. But if they don't stick around very long, then I could have a mix of both stimulated emission and spontaneous, right? So watch what happens if I increase the lamp control. Now there are a bunch of photons coming in, and we can see clearly the difference between spontaneous emission, which means in random directions, or a stimulated emission, in which case we see a pair of photons walking off to the right in the same direction as the electron that stimulated the emission in the first place. Okay, so one more time. There are two controls here. And let's go back, turn this down. And we'll actually going to reset all the conditions. Okay. From this point of view, I'm going to turn on the lamp control a little bit. And we can see that we have good stimulated emission of radiation. But occasionally, if the next photon doesn't come along fast enough, then we're going to get spontaneous radiation. Now let's go to the multiple atoms and see what's up there. So now we have a whole bank of lamps ready to illuminate this pile of electrons here. And then we have two states. So the basic idea is that we can turn the lamp on. And right now the lamp is set to pump electrons all the way up to the third state. So these photons need to be pretty short wavelength and pretty good frequency in order to have the possibility for both stimulated emission and spontaneous. All right, now when we take a look, we can see that some of the single photons that are going off are the result of spontaneous emission, but all the pairs that are leaving are a result of stimulated emission. So we can favor the stimulation of radiation by putting some mirrors. All right. Let's take a look at what's happening with populations. Even though the lamp light has enough energy per photons to kick an electron all the way up to the third energy level, they are collapsing down into the second level, and they might collapse all the way down to the first. But let's do the following. Let's suppose that we don't let them stay very long in this third excited state. So let's just turn it off. Looks like a lot of so it looks like we have a mix of both, really. So spontaneous emission and then stimulated emission. I'm going to throw some mirrors on, and what mirrors do is they're going to throw light back in the same direction it came from. And the advantage of that is that if we have a photon that's capable of stimulating emission from energy state 2 down to the ground state, and we can capture those and bounce them back and forth so that we keep pumping with external light, but we're populating that second energy level so that there are lots of available spontaneous to make, or there's going to be enough stimulated emission to do some lasing. And you can see that's the lasing that's happening right now. Okay, well, we have a pretty good lasing setup here, but it looks like we're going to have to let out some, otherwise we're probably going to get too hot. And now we're lasing. Okay, I hope that was helpful.